Mass spectrograph. A mass spectrograph is used to measure the masses of ions or to separate ions of different masses. In one designed for such an instrument, ions with mass m and charge q are accelerated through a potential difference V. They then enter a uniform magnetic field that is perpendicular to their velocity, and they are deflected in a semicircular path of radius R. A detector measures where the ions complete the semicircle, and from this it is easy to calculate R. Part A: derive the equation for calculating the mass of the ion from measurements of B, V, R, and Q. So in this design, we have this charged particle, charge Q, that is entering with zero initial velocity this region with a constant electric field. There's a potential being applied. This is the positive terminal, negative terminal. So it is repelled from this side, attracted towards this side. So it gets accelerated and gains a final velocity v, then enters a region with uniform magnetic field pointing out of the page. Our right hand forefingers point in the direction of the velocity. We curl them towards the direction of the magnetic field. That shows us the direction of the force, Lorentz force, QV cross P. If we do it during the semicircular path here, V cross B, right hand forefingers in the direction of B, curl them towards B out of the page. The thumb points towards the center, so we see that this is performing circular motion. When it completes the semicircular path, it reaches the detector. Okay, so the Lorentz force FB is Q cross product of velocity with the magnetic field, uniform magnetic field B. So QVB, because sine 90 is 1, velocity and the magnetic field are perpendicular to each other, is equal to mass times the centripetal acceleration mv square divided by capital R. So I can see that these v's will disappear and I will be left with the speed of the particle to be equal to QBR divided by m. At the same time, it's gaining a kinetic energy when it's subjected to this potential difference. The kinetic energy it gains is 1/2 mv squared starting from rest. And the kinetic energy it gains is equal to the potential energy supplied by the battery, which is QV. Q times the capital V. So we see that 1/2 mv squared. For V, I substitute QBR over m. So Q squared V squared R squared over m squared is equal to Q times the potential V. Now you can see that one of the m's will disappear and one of the q's will disappear. And I will find that the mass of this ion can be written as m is equal to Q B squared capital R squared divided by twice the potential V, potential difference V. So that's the mass of the ion. So in part A, we were asked to find the mass in terms of B, V, R, and Q, and that's what we have found here. In part B, What potential difference V is needed so that singly ionized carbon-12 atoms will have radius of 50 centimeters in a 0.15 Tesla magnetic field? So we will plug in some numbers to the answer we have found in part A. The radius of the semicircle we're looking for is 50.0 centimeters. The magnetic field that's pointing out of the page is 0.15 Tesla in magnitude. What is the mass of one carbon ion? It is 12 grams, 12 times 10 to minus 3 kilograms divided by Avogadro's number, 6.02, 10 to 23. And the charge is 1 electron charge, which is 1.6 times 10 to minus 19 coulombs. How do I know that that is the charge? It is singly ionized, so it loses only 1 electron. Okay. What potential difference is needed? That was the question. Now, looking at this answer here, the potential difference that you would calculate is QB square R square divided by twice the mass of the ion. So that's the answer we will use to calculate the potential. And this gives me V is equal to, now let's plug in the numbers. For the electron charge, 1.6 10 to minus 19 coulombs. Magnetic field is 0.15 Tesla. We take the square of that. The radius is 0.5 meters squared. And then we have twice the mass. The mass was 12 10 to minus 3 divided by Avogadro's number. So Avogadro's number goes upstairs, 6.02 10 to 23, and 24 10 to minus 3 kilograms. So the voltage we calculate here, the potential that has to be applied, is 2.26 times 10 to 4 volts or 22.6 kilovolts. That's the potential we will need to achieve this task. Now let's move on to part C. Suppose the beam consists of a mixture of carbon-12 and carbon-14 ions. If the potential V and magnetic field B have the same values as in part B, calculate the separation of these two isotopes at the detector. Do you think that this beam separation is sufficient for the two ions to be distinguished? Assume the atomic masses of the isotopes in atomic mass units are equal to their mass numbers 12 and 14, and one atomic mass unit is 1.66 10 to minus 27 kilograms. Alright, so now in part C, I have a mixture of carbon-12 and carbon-14 ions, two different isotopes. The radius R can be calculated again using the expression I have found in part A. The radius R is 2m times the potential V divided by QB square inside the square root. In other words, it is 1 over B, 2mv over Q inside the square root. So R is 2mv over Q square root times 1 over B. You can see from this expression. So let's calculate the radius for the carbon-12 ion. For carbon-12, I'm going to use 2mv, 2 times, what is the mass of one carbon-12 ion? 12 times 10 to minus 3 kilograms divided by Avogadro's number, 6.02 10 to 23, because it's the mass of 1 mole, multiplied by the potential I have calculated, 2.26 times 10 to 4 volts, divided by the electron charge, 1.6 times 10 to minus 19 coulombs. This is inside the square root, multiplied by 1 over the magnetic field, 1 over 0.15, and that gives me 50.0 centimeters for the answer, because it's the answer I have used in part B. Now, how about the radius for carbon 14? Now, if I write it explicitly, this will be 2 times 14 10 to minus 3 kilograms divided by Avogadro's number, multiplied by this voltage, 2.26 10 to 4 volts, divided by the charge, 1.6 10 to minus 19 coulombs. It's singly ionized, inside the square root, multiplied with 1 over the magnetic field. Now I see that if I take the answer for R12, divided by square root of 12 and multiply it by square root of 14, I will have R14. So this is actually R12 multiplied by square root 14 divided by square root 12. So that's the simple observation. So with that, I can calculate the difference between R14 and R12. The difference between these two radii turn out to be 4.0 centimeters. Now you can see that for the carbon 12 here, it draws the semicircle to reach the detector. The diameter is twice R12. And for 14, carbon 14, it draws this semicircle so that the distance between the two endpoints of these semicircles, delta r, is actually the difference between the diameters of these two semicircles. So from this simple drawing, I can see that delta r is actually twice R14 minus R12, which is going to give me delta r is equal to 8.0 centimeters, easily detectable. So we can easily distinguish these two ions. All right. So in the case of the mass spectrograph, we're using an equipment which measures the masses of ions by accelerating the ions inside in a potential difference, and then they enter a region with uniform magnetic field perpendicular to the velocity of the ions, so that they draw a semicircle and the ions are detected by a detector at the end. Now, they are subject to the Lorentz force inside the uniform magnetic field, and velocity and magnetic field are perpendicular, so QV cross B magnitude is QVB. The direction is radially inward, so it's going to draw a semicircle. From this uniform circular motion, QVB is mv squared over r, and the speed is QBr over m. The kinetic energy the ion gains inside this potential difference is 1/2 mv squared is equal to QV, assuming that it starts at rest. And from this, I can calculate the mass of the ion. The potential is QB squared R squared over 2m from this expression. And for some given values here, we find that we need a potential of 22.6 kilovolts potential difference between these two plates in order to accelerate it to reach this speed. Now, if I use carbon 12 and carbon 14 ions, the radius of the semicircle they will draw is 2mv over qb squared inside the square root. So for R12, in part B, I have basically determined that this should be 50 centimeters. For R14, from this expression, I see that it's 50 times square root 14 divided by square root 12. That's the only difference between the two radii. So the difference between them is 4 centimeters. But the difference on the detector side is, as you can see here, is the difference between their diameters, which is 8 centimeters, and that can be easily detected. So these ions can be distinguished easily.